Okay, I have an important thing. After class on Friday, Yari came up to me and she talked about, we haven't covered this yet. Should we still cover it in our presentation? I was like, oh yeah, I'll get to it. And then I realized that today on the schedule is supposed to be a review. I can't get to it during the review. And we really have 2 lectures worth of material that, in theory, I would like to have in this exam. That is their scheduled material for the exam. And so I want to get the students' input. I've already talked to Connor and Daniel about this, about one of 2 options. Option number 1, and this is the one I prefer, but not the one that those 2 gentlemen preferred, is to postpone the exam until the week after break. So basically, we come back and have the student presentation on Monday and the exam on Wednesday. Option number 2 is to cut this material out of this exam and just have it hold over to the final exam. And then have the exam on schedule. So, of course, if I was thinking, I would have made a clicker question on this and it would have been a complete error. Did you say you had a click question? Or no? Believe it or not, the clicker thing still hasn't even come up, so I'm just going to make my own. And what's your question, Yari?
Well, it's not a question. I just have something to say about it.
I have something to say. Okay, it's now lobbying time.
The thing is that if we just cut the section and still do the test this week and the presentation this week, that means that what I had to say now has to be switched and all our group has to be
That's
switched.
true.
And the presentation is on Wednesday.
Because I told her on Friday.
So I don't have a lot of time left to change it all up. But we'll see what everyone says.
Could I do a filibuster just to avoid this topic?
A filibuster? No. Wait. You may speak to the topic. You may not read a children's story that is non-germane. So go ahead.
Oh, it's okay.
Children's story about what?
I was just wondering if I could do it.
Well, no, we can't have a filibuster because we don't have Robert's Rules of Order. All we need to break the filibuster is me saying, okay, moving on.
Dr. Webb,
Yes.
where exactly did you get to the lecture on Friday?
I am just, well, yes, but I didn't get to where it says in the syllabus.
Oh, yeah.
I am just ready to start on, let's see, let me look through my review thing here. Okay, I'm ready to start on Unit 60.
So it looks like that the test in the syllabus, it says the test is from 51 to 70. So there's still 10 units of things that
Yeah,
test that we haven't gone over.
that's right.
Okay.
Can you just pull up this week?
That you can't see this. Well, let me hide that and then B change it so you can see it. Okay, and now that Tioni's here, everyone but Russell's here. Russell stepped in for a minute, but then he stepped out. Choose away. And based on your question there, I knew which sections to put. Obviously, you can see how it's breaking down. I took off the people's names so you can't see who's not voted yet and try to correlate.
Oh, well, I just like to see where. I always like to see that upside vote.
I was waiting for it to be tied, and then. We should have at least. We only have 9 votes. 2, 4, 6, 8, 10, 11.
Oh my goodness.
Test on what?
Okay, Aldo, now it's your turn.
No, now everybody knows.
Don't do Wait, test on Friday or test on Wednesday?
Oh wait, you still gotta vote.
Well, I already have a test on Wednesday, so I'll do it Friday.
I mean,
No, this is
not
after
this
the
one.
Wednesday after break.
Oh,
oh no.
What is-
I will
what is
tell
the
you that I'm
possibility?
voting for the top one because I will not remember this material
After the break. Okay, so I'm going to take it then that, I mean, if it's 50-50, we're still going to do it on schedule because I don't like people to have prepared for this exam and then like,
the scheduled test is this Friday, right?
That's correct.
Okay, we're doing it Friday.
Okay, so got that out of the way.
All my sections.
I'm sorry, Yari. I will be understanding if no one else. Okay, that said, then let's get to the review. Yari, you can still do that material. Okay. So, what is going to be on the test? We're going to learn about our sun and stars, classifications of stars. So, number 1, make sure you know the parts of the star, going from the core, which is where fusion occurs, out. What's the first zone called after the core? The radiative zone. It's called the radiative zone because you have such high pressures, you don't really have convection currents flowing. And it takes like 100,000 years for energy produced by fusion in the core to make it to the edge of the radiative zone.
So,
Now that's a statistical calculation, it's an average time question.
so with the cause that you have the convection, is it faster for them?
Once you get into the convection zone, it's much faster because then
No,
Well,
because one like the stars that automatically.
Yes. once you get into the convection zone, it's much faster because even though you still have a random walk, the entire matrix is floating upward. And so it only takes about a month to get through there. So the question Russell was asking, because Russell's jumping ahead, he still wants to know how it gets so hot for a white dwarf, which is part of the material that we'll move to the next test. Some stars have complete convective mixing. Small stars have complete convective mixing, which means that it doesn't take very long for energy to get from the core to the surface. But it also has a real big effect on when they die. Because when they die, there's essentially no hydrogen left, and so they can't make the shells that we're going to learn about that make a giant star. So stars that have small masses have complete convective mixing. Energy gets out quickly, but when they die, no giant.
Don't they also like last long?
Yes, because we went over that. That's one of the things that would be on the test coming up in the last section, the part that Max wasn't able to be here for, that the lifetime of the star is inversely related to the mass. The more mass it has, the shorter its lifetime. Because the luminosity, which is telling us the rate at which it is burning, fusing, fuel, is proportional mass raised to the 3/2 power. And its fuel is proportional to mass. So that means that the time it takes to burn out is proportional to mass divided by mass to the 3.5 power, or 1 over mass to the 2.5 power. So a more massive star has a much shorter lifetime. So our sun is calculated to have a lifetime of about 10 billion years. How do they get that? They say this is how much hydrogen it started with. This is how rapidly it's fusing hydrogen to helium. In 10 billion years, it runs out of hydrogen. The sun is right now, they believe, about halfway through its lifetime. And once again, that would have come up in the next 2 lectures on why they believe the sun is halfway through its lifetime right now. Okay, so we have the radiative zone, then the convective zone. How do we know the sun has convection?
Granules.
We see the granules on the surface. The granules are direct visual evidence showing us convection. We actually can use the Doppler shift to see that the hot regions are coming up toward us and the cooler regions are moving away from us. which tells us we have convection. So it's directly observed. On the surface, we have things like a sunspot. What is a sunspot?
Oh my gosh.
Basically, that's cooler than the surrounding area.
Okay, it's cooler than the surrounding area. Now, we've gone through this enough, we even know why it's cooler. Why is it cooler than a sunspot?
Magnetic field is like this compressing the heat, then the gas down, and so it's cooler.
Yes. Now, the actual mechanism is a physics mechanism. It's not allowing things to move freely. And so that's how it's depressing, not allowing high temperature material to flow up. And so the strong magnetic fields in those sunspots is depressing the temperature. And so the temperature in those sunspots may be 4,000 kelvins instead of the roughly 6,000 kelvins of everything else, which is still super hot, but compared to the rest of the sun, it's not. Okay, keep going out. What's the next layer above? Well, what do we call the surface of the sun? Photosphere. Photosphere because that's where light comes from, photo, light. You go up above the photosphere, and what's the next region called? It's for color.
What's it called? That
Chromosphere. And it's called chromosphere because it has a pinkish color, because you can see, if you block out the sun, you see hydrogen emission lines in that region. You go up further, then you have what I think Aldwin was saying, or no, what Max was saying, the corona. It happens to be the city I was born in. It means the crown. And that crown is like 1,000,000 kelvins. What temperature is the photosphere? Like 6,000 kelvins, 5,800. And so it gets much hotter going up. And so there's been a lot of study to try to figure out how you could possibly get hotter going up. And the belief is that it is the magnetic fields accelerating particles up there, making it so it's hotter out there. And then the corona extends for a very large distance. It basically is up to the person where they decide the corona ends. You could say that because we are receiving radiation, there are particles from the sun that are hitting the earth all the time, constantly, that we are within the corona. It would be a viable definition. Generally, nobody would use that as the definition. It would be viable. So those are the layers of the sun. And we talked about the weather on the sun, the magnetic cycle. Are these magnetic cycles important to us as we study other stars? Not really. But they will become important to us as we study what happens when stars die. And we'll see things where the magnetic fields come into play. But they're not really important. The sunspot's not really important when we look at other stars, but they're really important for us on Earth because they tell us things about, when the sun has lots of sunspots, even though the sunspots themselves are cooler, the regions around that hot material has to go somewhere. It goes around and it actually gives off more radiation. So when you have a lot of sunspots, the sun gives off more radiation. We receive more radiation. It causes temperature on Earth to rise, generally speaking. Less sunspots, less radiation from the sun, temperature on Earth tends to drop. And in our recent history, recent being a few hundreds of years, we had a much cooler temperature on Earth because solar activity basically was stopped in the Middle Ages. So we have all of this about the sun. I see that I forgot to change this back to the review slide. You have access to these, of course. So we have all these things about the sun. There are a few things I didn't talk about. I didn't talk about a spicule, a flare, a coronal mass ejection, a prominence. So let's talk about what those things are. The spicules, what are those?
It's like the jets of gas that shoot into the corona.
Well, they're the little jets that kind of look like prairie fire. On the surface of the sun, you have, especially around sunspot areas, you'll see it looks like, fire in a grass field. And that's little jets going up. The bigger jets are the prominences. So prominences are the big arcs going like this. And then when those things break, you shoot off a flare. And oftentimes that flare will then result in a chain reaction, or so it's believed by some, that causes the coronal mass ejection, which is where a huge amount of material from the corona gets ejected. And of course, we saw in that video how devastating this can be if it were to hit the Earth. We have them hitting the Earth fairly commonly. When we see pretty auroras, that's because we had something like a coronal mass ejection aimed at the Earth, and so we had this additional solar wind that caused it. But in 59, there was a coronal mass ejection that hit the Earth that was so large that it caused significant problems with their telegraph and significant northern lights that is believed if that were to happen now, it would be devastating to civilization. We'd be out there with our pitchforks protesting or something.
Riding.
Yes. This equation here is the ideal gas law. It just says that there's a relationship between the pressure, the volume, and the temperature. And that has important ramifications, but I don't think that's going to be on the test. The source of the sun's power. How does the sun produce energy? Fusion. It's not making energy. I said the word produce, and produce sometimes you think means make. I mean, sometimes it does mean make, right? But when I say it here, how's the sun produce energy? What it's doing is converting energy from mass into, light. And so it's using that equation there, E equals mc squared, that's Einstein's equation, is what we can use to explain how the sun is converting mass into energy. You did a homework problem, you saw the sun's converting about, somewhere in the ballpark of 1 billion kilograms, what was it, a second? It was some short period of time. And you think, wow, it's going to run out of mass really soon. Until you look at the mass of the sun, which is 2 times 10 to the 30 kilograms. It's got a really long time because that's a real small fraction of its mass. So we have nuclear fusion with what's called the proton-proton chain. So we went through the sequence of 2 protons collide. You have a complicated interaction which destroys a proton, creates a neutron in its place plus a positron and an electron neutrino. And so the positron and the neutrino, the positron is going to annihilate with electron energy. The electron neutrino, those come flying out, they go right through us. Then you have the helium-2 is what's left. The helium-2 meets another helium proton, another hydrogen, not helium-2, hydrogen-2. The hydrogen-2 meets another proton, and you get helium-3 plus photons, and finally, 2 helium-3s collide. You get a helium-4 plus 2 hydrogens and more photons. So you get energy coming out. The net reaction is 4 protons, makes a helium-4, plus a bunch of energy. So that's the sequence that scientists came up with less than 100 years ago for how the sun is staying up there. How it's producing energy and not just cooling down. And so scientists, remember scientific method, sit down and say, okay, we've got this theory on how it works, and it says we should be producing this many neutrinos per second. And so they set up big neutrino collectors on Earth, and what did they find? What? Only 1/3 as many neutrinos as was expected. And so, with only 1/3 as many as expected, they were like, maybe we were wrong. Because the whole scientific method says you look at the predictions, and if the predictions are disproven, you have to go back and consider how to change your hypothesis. But in the end, they were wrong about something completely different. They were wrong in their understanding of the neutrinos. The neutrinos come in 3 flavors, and they can shift between them. At that time, they didn't think they could shift between them. And it wasn't until the 1990s that experiments solidified that the neutrinos can shift between types. So that's a fairly recent discovery to bring it back into shape. So now we're really confident that we have that photon-photon fusion. Photon, photon, proton, proton. Whew. The H versus R is a world of difference, friends. Proton, proton. You can't fuse photons. Okay, so that covers most of what we have here. So I'm just going to move on. Does anybody remember what the Zeeman effect is? Nope. The Zeeman effect is how we know for sure that those sunspots are magnetic. Right? You can say it looks like a duck. Acts like a duck, it must be a duck. But when it has the Zeeman effect, you have verification that it's a duck, that it's magnetic. Because the Zeeman effect is you look at the emission lines, and when you put them in a magnetic field, those emission lines will split into multiple emission lines. And the amount that they shift is proportional to the strength of the magnetic field. So by measuring the shift in wavelength, they can determine the strength of the magnetic field. Not just is it magnetic, how strong is it? So we have a good measurement. How do they know about the Zeeman effect? Because it was theorized on Earth and it was observed on Earth. And then we take that knowledge and we apply it to the sun. What does differential rotation mean?
It's rotating at different speeds at different places.
Different speeds at different places. And we saw that for the sun, it rotates faster at the equator and slower at the poles. And we also saw from the video, this was not in our textbook, that it rotates faster inside and slower outside. So with that different rotation, we can explain the sun's magnetic cycle because magnetic field lines start getting tangled up because of the differential rotation rates. And so the magnetic field lines start getting tangled up, which makes them deform and come out of the surface, making sunspots. And eventually they create enough force on the rotation that it just causes everything. It's, to me, I just think of it as Control-Alt-Delete on a keyboard, you know. Of course, these days, Control-Alt-Delete isn't the same as it was when I was a kid. Okay, when I was a kid, there were no computers at home, but when I was in college, Control-Alt-Delete was an instant reboot. It didn't bring up anything. And that's what I view as what's going on there. You just get so much things haywire that it just reboots, starts over with the whole cycle. So we have that solar cycle that occurs about every 11 years. You have a reversal. The magnetic fields, the poles reverse. So the north pole of the sun becomes the south pole and the reverse. Okay, looking at the stars. How do we know the difference in the stars? The difference, the distance. The methods of knowing the distance to the stars is important. And we've only gone through some of them so far. We talked first about triangulation. That is, Latifah is to the right of Gabby. And if I come over here, now they're right in front of each other. If I know how far I moved and I measure that angle, then I can tell you about the distances. If Gabby's far enough away, then I can tell you how far away Latifah is from measuring that angle. That's what triangulation is. It's using parallax. And so that's the first way of determining distance. Well, there is a new way. That's the first way because that's what the ancient people were really able to do. Now we can send radar. So we can measure the distance to the sun by bouncing light off of the sun. So we can get the distance from the Earth to the sun real accurately that way. For something like the next nearest star, Proxima Centauri, I don't think we can bounce radar off of it. It's 3.4 roughly light, or 4.3 roughly light years away. It's going to take a while for that radar to come back, and it's probably not going to be very reliable. So for that, we have to use something like triangulation. Using parallax, you should be able to use this parallax equation. Wow, that's perfect. This parallax equation, the distance in units of parsecs is equal to 1 divided by the parallax angle measured in units of arc seconds. The parsec is simply a parallax arc second. It's the distance an object must be away for us to see a parallax angle of 1 arc second. And turns out that you have the conversion factor 206.265 astronomical units is 1 parsec. So I didn't talk about this equation here, so let's not worry about it. That's for transverse motion for something that's going like this, and how we can relate its distance and its angular change to its speed, but I never used it, so we won't cover that. Oh, wait. Yeah, that was the bottom. Good. Okay, next, getting to the stuff, I spent a lot of time on the sun. Not nearly as much stuff on the next things. So, brightness. What's the difference in luminosity and brightness to start with?
It's called luminosity is how much the star produces.
Luminosity is how much energy per second the star produces. What's brightness?
How bright is the star? How much? Like what we see.
What we see. Just make it simple. The brightness is what we see. So if something's closer, it's going to appear brighter. If something's farther, it's going to appear fainter. But the luminosity is how much light is truly giving off. And so that the luminosity is a function just of the object's size and temperature. Hence the equation up there, well, I guess not up there. There should be an equation somewhere that tells us the relation, but not there. The luminosity just depends on the area, which is dependent on the radius squared, and the temperature, specifically the temperature to the 4th power. So the luminosity is area times the constant times the temperature to the 4th power, or 4 pi times the constant times radius squared times temperature 4. So luminosity, those two things. Brightness also has the distance, because if light is spread out over a sphere, the area of the sphere is 4 pi radius squared. And so the equation, the top one up there, brightness is luminosity divided by 4 pi L squared, where L is the length between the two objects. Why is it L instead of R? Well, it's just L instead of R because instead of saying we have a sphere of radius R, we say we have a separation of length L, which defines a sphere of radius L. So with that, the brightness drops off with distance squared. So if I'm twice as far away, let's say that Max and Aldwin are putting off the same amount of light, but Max is about half the distance for Aldwin, so Aldwin's twice as far away. If they're putting off the same amount of light, Aldwin's going to be 1/4 as bright because 2 squared is 4. And so using that relationship, we were then able to get mathematical equations for the magnitudes. Magnitude, we have apparent magnitude that tells us about how bright it is. Absolute magnitude, which tells us about its luminosity. The absolute magnitude is equal to the apparent magnitude if you were a distance of 10 parsecs away. So it's taken out that how far away portion. So remember the magnitude scales. The first order magnitudes were the brightest. The 6th order magnitudes were the faintest. They're now set to a mathematical relationship where a difference of 5 corresponds to how much difference in brightness? 100 times difference in brightness. So a 6 is 100 times fainter than a 1. What's 100 times brighter than a 1?
Oh, 5.
0, 1, 2, 3, 4. Okay. 0 is a difference of 1. Yeah. It would actually be 4.
Oh, it's what to get to that.
There's a difference of 5 between the two numbers. Just like 1 and 6, a difference of 5. But that's right. You go to the minus and you're just getting brighter and brighter and brighter. Now this reminds me, the moon right now. What's going on with the moon? Not a review for the test at this moment. What's going on with the moon?
It's close to the earth.
Okay, for a full moon. So we have the quote supermoon, which is some astrology term somebody made up, and then people have morphed it from here to there and everything. What?
Like most of astrology.
All that supermoon means, well, it's nebulously defined. Some people say it means that it's in the closest 10% of its orbit to the Earth, right? Because it's in elliptical orbit. And so they say, well, it's got to be the closest 10% at full moon. Other people say, oh, that doesn't happen often enough. We want to have supermoons more often. Let's make it in the closest 50%. But the full moon right now, because the eccentricity of the moon varies over time because the other planets have an effect on the Earth and the moon. We're in a stage where the moon is somewhat more eccentric in its orbit, and we're having a full moon when it's at perigee, at its closest distance. And so, is it going to be any more cool than a normal full moon? A little bit, not much. It's nothing to get super excited about, but everybody does because they say, ooh, super moon, that must be special.
That's the thing. If you tell somebody it's going to be bigger than that, just like when I tell somebody, oh, I changed the bakery recipe, I didn't change the bakery recipe. It's the same.
Don't
It's all in your
ruin my world.
Occasionally I do change the recipe.
That's going to be good
That's
tomorrow.
not actually.
If lab's not good tomorrow, then I'll have a chance to lecture some more.
Like just because the moon's on.
Oh. Okay, so moving on then, we have a mathematical relationship. The hardest math in the entire class is that mathematical relationship that you see there relating lowercase m's are apparent magnitudes, relating brightnesses. And so the difference between the lowercase m's is equal to minus 2.5 times log of the ratio of the brightnesses. Or you can have the second equation there, the difference between the absolute and the apparent magnitudes has to do with the distance. And so you have that relationship 5 log of the distance divided by 10. Or we usually put it in the bottom form, the distance, you can tell the distance to a star if you know its brightness, its apparent magnitude, and if you know its luminosity. So certain objects, we know their luminosity, like certain, I mentioned this in class when I talked about the certain supernovae are always the same luminosity. And so if they're always the same luminosity, if we see one, we can measure its luminosity, or excuse me, its brightness, and then use that equation to determine how far away they are. And so that's another way to determine distance, is if you know the luminosity and the brightness. There's another way for us to get the luminosity. That other way is by using the HR diagram. The HR diagram, if I know a star is on the main sequence, and I know what its temperature is, I can identify what its luminosity is. And if I know its luminosity, I know its absolute visual magnitude. Well, I just measure its apparent magnitude here on Earth because that's what apparent is. It's what we can measure. And then I can determine the distance away. So I think you have a homework problem that has you doing that. Has you calculating the distance of stars away based on where it is in the HR diagram. So that would be using the bottom equation. Scroll on. Make sure you know both the spectral types and the luminosity types. So spectral types, what are they? Name them in order from hottest to coldest. Right. It's a very simple mnemonic. Oh, be a fine gal, kiss me like this. Or oh, be a fine guy, kiss me like this. Whatever. It's simple to memorize. And those are telling us about stars. What is an O star? It's a super hot star, one that's 30,000 kelvins or more. What's a B star?
Also,
But not as hot. somewhere between 10 to 30 kelvins. And what about an A? How much?
Is it like 7,500 to 10,000?
Okay, about 7,500 to 10,000 kelvins. That was A's. What about F's? Or no, that was F's. Excuse me. That was F's. O, B, no. Okay, gotta get straight in my head. 10. No, okay, that was A's. That was A's. So what's an F? Six to 7.5. And what's a G? 5 to 6. K?
Like 3,500 to 5,000.
I believe that's right. And then for M, don't worry about the temperatures for L's and T's. M, so then will just be below 3,500. So we have the temperatures are tied to those letters. Where's the sun?
G.
It's a G. More specifically, it's got a number following. It's a G2. A G0 would be the hottest of Gs, which would be 6,000 kelvins. A G9 would be the coolest of Gs. And so the G2 is 5,800 kelvins. So make sure you know what those are. Know what the numbers are and how they relate to temperature, or letters are and how they relate to temperatures. And then we have the luminosity classes. What luminosity class do 90% of all stars fall in? The main sequence. And what is the classification? It's a Roman numeral for the main sequence. 5, Roman numeral 5, which is a V. So we say that the sun being a main sequence star, is a G2V. So we have our spectral class and our luminosity type both there for the sun. So what are the other luminosity types? Okay, Roman numeral 4, 3, 2, 1A, 1B. Would you believe? But what are those? You should know what they are and where they fall on an HR diagram. So 4s, that's IV, are subgiants. 3s, giants. 2s,
Mini giants.
2s are bright giants. 1B are supergiants, and 1A are bright supergiants. So they just go up, and now we have the HR diagram. We have to know this HR diagram. So you need to know what is on. I'm going to make a new page instead of trying to slip it in here. Insert. Okay, what is on the, hey, look, I killed the pin. Please work. Wow. Okay. My experience says if I kill the whole thing and come back, it'll work. Failed to kill it because I don't have the patience for this. Okay, at least my experience was right. What's on the horizontal axis for an HR diagram? Temperature. And where do I find cold temperatures? Cold temperatures are to the right. So over here is cool. So that might be, let's say, 2,000 kelvins. And over here is hot, maybe 30,000 kelvins. Oftentimes you'll see an HR diagram, and on the top of it, they will have O, B, A, F, G, K, M. because those tell you the temperatures as well. Okay, what about the vertical axis? What's on the vertical axis? That's the luminosity. In solar luminosities, that is, if the luminosity is equal to the sun, that's a 1. Where is low luminosity? Where are they not very luminous? The bottom, that's right. So this is low luminosity. Up here is high luminosity. So we have 1 for the sun, somewhere here in the middle. And then we have 0.1, 0.01. Excellent, that's my hand. What do we call an axis with the numbers like I just showed? Hint, it's not linear. It's a logarithmic axis. So that the same change in vertical height is a multiplicative factor. So you go up the same distance, you're multiplying by 10 from one line to the next. Not going up by 10, multiplying by 10. So that means the difference between the two lines near the top is a much, much bigger difference than between two lines at the bottom. So the sun being a G2, the sun is going to be close to here, and a luminosity of 1, so it goes like this. And so we'd find the sun there. And the sun, we've already said, is in the main sequence. So the main sequence goes something like this. And it's actually a band. It's not a straight line, it's a band. You probably noticed that it was kind of fuzzy or something on the graphs. The stars start on the main sequence down here, and then they burn their way across the main sequence. So they move within that band as they age. So that is our Roman numeral 5. Okay. Bad. There it is. So this is Roman numeral 5. So where am I going to find Roman numeral 4? First, let's start with, is it above or below the main sequence? It's kind of important. Above. Everything that's a living star is above the main sequence.
Anything that's above us is our sun. Isn't our sun 1?
Our sun is a 5. I'm not talking about luminosity. I'm talking about its luminosity class. So these here are the subgiants. And then where do I find the Roman numeral 3s? This is stuff you need to know. There probably will be a problem that has you identify things on the HR diagram on the test. Not to mention, at some point, we have to have a quiz where you have to draw an HR diagram. So where do I find Roman numeral 3? I'm really glad I was going to give you this as a quiz today.
Isn't that like the giant?
Yes. And then Roman numeral 2. Whoops. This one was B. Bright supergiant.
What about the stars below the main sequence?
Okay, what about the stars? There are items below the main sequence, and they fall like this. And those are white dwarfs. So they don't have a luminosity class because they're not stars. They're objects. They're not stars. They used to be stars, but now they're dead. And so when we get through the death of stars, we'll see where they come from. We'll see why they're hot. Because you can see they're over here on the hot side of the spectrum, or of the HR diagram. So we have luminosity, temperature. We can place the stars on there. How can we tell the radius from this diagram?
Maybe like seeing where they fall into in terms of luminosity and temperature, then plugging that into a certain equation, which I do not know.
There's the equation. He's absolutely right. So we can find the radius just taking this and solving it for r. And so that's the radius you can determine, and it gives us lines of constant radius. And the lines of constant radius are lines that go like this. And so radius is increasing as you go up into the right-hand corner. So up here is the largest radius. So when we start talking about giants and red giants, we can now identify what makes a red giant pretty simply. Red giants are going to be things that are large in radius. And so large in radius is going to mean somewhere in the ballpark of from here on out. And red in color, which means from here on over. And so anything that's in this region here is a red giant. And actually, oftentimes we consider these red giants here as well, but they're smaller giants, right? Not as big. So we can see where red giants fall in the HR diagram. Oh, darn it. Fall in the HR diagram if we understand what the HR diagram is. So make sure for the exam you know what that HR diagram is and how to interpret it and read it. Okay. This equation that you said you didn't know that I just wrote, that's the Stefan Boltzmann law. So that's what that one is. And you can see that it's written right here. Okay, last sections. This equation I just talked about as we started class, relating the lifetime of a star to its mass. Because the more mass it has, the faster it burns its fuel, the more light it gives off, and thus the shorter its lifetime. And that brings us to, actually, it's through 59, not 60. So that's as far as we go, through 59. Question, Gabby?
What's the question at the end going to be?
I think it might be about, I have to look it up. I don't remember. But yes, do look that up as well. We can mention it in lab tomorrow. All right.